Sri Lanka is in an active dengue outbreak. Roughly 87,500 cases have been notified so far this year, and the National Dengue Control Unit has designated 137 high-risk MOH areas. Every week, the Ministry of Health has a fixed number of vector control teams and has to decide where to send them. That decision is made largely reactively. Teams follow reported case surges, but by the time a surge shows up in the weekly notification data, transmission has already been running for 2 or 3 weeks. Mosquito infection, the extrinsic incubation, human infection, symptoms, care seeking, and finally notification. Reacting to notified cases means arriving late after the outbreak, not ahead of it. We built a decision support system platform to close that gap. We built Dengue Sentinel with taking multiple things into consideration. The massive gap of Sri Lankan health system not being able to bear the severe load caused by the dengue epidemic, which has been surging through the countries over the past few months. So let me tell you how exactly it aligns with UN's SDGs. This is a health system problem, but it's also a climate problem and an equity problem, which is why it sits across 3 UN Sustainable Development Goals. SDG number 3, good health and well-being, directly, earlier warning, and smarter resource allocation means fewer cases and fewer preventable hospitalizations. SDG 13, climate action, dengue transmission is rainfall and temperature driven. This platform treats climate data as a first-class forecast input, not as an afterthought, because a warming, wetter Sri Lanka is a higher dengue risk Sri Lanka. SDG 10, reduce inequalities. The allocation engine has a hard flow guaranteeing every high-risk district gets some coverage, so vector control resources don't just flow to the loudest outbreak, where smaller, poorer districts get unserved. Because currently in Sri Lanka, we see a massive problem where more urban areas like Colombo, Gampaha, Kandy, and Galle gets more attention, whereas more rural areas don't get that attention because the surge is much smaller. Moving on, let me show you exactly what we built. Getting ahead of an outbreak means answering 3 genuine different questions, and we treat it as 3 separate stages rather than one black box model. Stage 1 is the forecast. Where will cases be in 2 to 4 weeks, and how confident are we? A probabilistic district level forecast, not a point guess. Stage 2, effect. How many cases does sending K vector control teams to district D actually avert? This is deliberately not answered by the same forecasting model because historically teams were sent to the outbreaks, so regressing causes on teams' weeks recovers a positive coefficient and a naive model concludes vector control causes damage. We break that by co-founding a mechanistic SCI-SIR compartmental model and intervene directly on the vector parameters, a genuine simulated do operation, not a correlated read-off based on history. Stage 3 is to allocate. Given a fixed weekly budget, where do teams actually go? An integer linear program because the returns to control effort saturate. The 10th team in Colombo averts far fewer cases than the first team in Gampa. Sorting districts by forecast case count and going down the list is the wrong answer, and we can show you why. Now let's move on to the demonstration. The dashboard is built around one idea, the same forecast scoped differently. For who is looking at it? Nothing is recomputed per request. Every number here comes from an artifact, a batch pipeline, all you wrote. So this stays usable at 2 a.m. during an actual outbreak, when a slow dashboard is much more of a liability. This is the first thing that every user sees regardless of their role. So firstly, we can see in the national overview, the district's forecast, the districts at high risk or above, the total forecast, cases nationwide, and the single highest risk district. The risk map indicates a map of all 25 districts and 4 tiers and color-coded depending on the severity of the risk. The risk has been divided into 4 main levels: low, moderate, high, and very high. Every district is ranked, which means that the same risk levels as a sortable bar chart, as we can shown in the full regardless of the map above, because a map alone hides the magnitude at the end. And as you can see here, the national cases was the observed versus the forecast. The solid line shows the real notified cases, and the dashed is the model's forward projection. So it's visually obvious where the observation ends and where the prediction begins. And also on the right hand side of the screen, you can see the rainfall and the dengue cases and how it correlates. And the two series are stacked because cases follow rainfall by roughly 6 to 8 weeks. Rain is a massive cause of dengue because it fills containers and which causes larvae to develop and adults to emerge, and then there's the transmission rise. This is a climate link made visible and not just model. So as you can see here, we can switch our role depending on what can be done. So currently we are in the public view. So in the public view, you can take a look at the districts, and on district level, what the situation is. And as you can see here, as you scroll down, you get a rough idea of where your district lies. And depending on the risk level of your district, you get a custom-based notification as to what you can do to prevent yourself. And you will also get a live forecast as to what things look like and where things stand right now. And you also get a recommendation system where you can go through the symptoms and what to do in case of an emergency. And the user obviously can subscribe to certain notifications depending on their need. Okay. So in the next listing, we'll move on to the hospital staff portal. In the hospital staff portal, you can see that it shows them what a hospital staff worker would want to see. A hospital staff worker currently will not be able to see how many people will actually admit to their hospital depending on what has been done. The main reason for this happening in Sri Lanka right now is because the existing systems fail to actually predict when and where the outbreak will happen. So the projected load and the admissions, the ICU patients, peak occupied beds and platelet units and additional nursing staff needed all are derived from the following forecast. And then as you can see here, the hospital administration will be able to see what the published clinical ratios are, which means that every single one of these cards is labeled a planning estimate, which is not a measurement, because the reason why we weren't able to use the real data like we did before was because Sri Lanka does not publish real-time hospital occupancy, ICU census, or platelet stock. So we show the honest gap instead of inventing a simple number simply because the numbers are not available. So you can see that there are four main tabs here: project load, supplies, facility map, and planning ratios. All of these are editable by the hospital so that they can substitute their own hospitalization rate, ICU rate, and length of stay instead of trusting a literature default. Meaning that they have the ability to interact with the system and make sure that they submit whatever number of submissions that actually happens in the end, making sure that the system is not just a decision-making system in the end. Now let's move on to the Ministry of Health or the Regional Health Officer portal. In the District Health Officer's planning vector control, they see these things. They see the hotspots, the operational risk map, scope to their necessary districts, and team deployment. How many vector control teams and where should they be deployed this week? The intervention plan, which is the stage 2 that we mentioned before. The stage 2 casual output shows that the projected cases averted per team sent per district. The actual, if we send a team here, this many cases don't happen number. The scenarios: a live SCI/SIR reintegration, a drag budget or team count sliders, and what's the compartmental model resolve in real time. This is a deliberate exception to never compute at request time. It's a live what-if tool, not a served metric. The budget shows a greedy water filling optimizer across 4 spending categories: vector control, awareness, hospital preparedness, and emergency reserve, showing which category is binding at each budget level. This gives them an option to maintain their budget, because currently a big issue in Sri Lanka is that when it comes to team allocation, it is done on a very inefficient way, where they aren't able to constitute for how much the budget is, and they aren't able to tell exactly how much can be allocated for each district and for each team. Now moving on to the next portal, which is the National Hospital Administration Portal. The Ministry of Health nationwide has an oversight configuration. Here it shows you the system health. It shows you when the pipeline was last. This shows you this shows you when actually was the last pipeline run and the panel source, and it shows the and which model produced this one particular forecast. The data sources, as we can see here, is a live table of every upstream feed, whether it's currently working, gated, or estimated. Meaning that this is not just simply based off one particular data set. This is always continuously updating with the dynamic nature of the epidemic itself. And the model of the stage one comparison table in the app is not just a README. It also has user and roles and audit logs, which gives access control models visible with an explicit note that this is a switcher and not a real login system. So these are not obviously implemented user roles with access levels, but rather it's what if we did actually implement this in the real world, what it would look like. So the four rows basically has one underlying forecast with no duplicated logic. The same district rank risk artifact is shown to each user to make sure that the user will be able to see what they want to see and what is required by their necessary role. So, moving back to the presentation. Now let's take a look at where exactly our data comes from. The case data comes from the weekly epidemiological report from Sri Lanka's epidemiology unit, and we built a scraper that auto-discovers every published report, over 1,000 issues, and a PDF parser for tables that turned out to use rotated, reverse text and a shape nobody had documented. Every past week is cross-checked against the report's own printed national total before being admitted to our panel. Our 234 recent reports, 147 passed that check, and 86 were excluded. And we manually verified those exclusions are genuine arithmetic inconsistencies in the government's own published PDFs, not bugs in our parser. The weather data was taken using Open Meteor's ERA5 reanalysis archive. Daily rainfall, temperature, and humidity per district centroid was free and required no API key going back to 2010. Boundaries and facilities were used OSHA HDX for the 25 district polygons, OpenStreetMap for 1,231 real hospital and clinic locations. Clinical ratios and bed density were published literature and World Bank indicators, always rendered as labeled planning estimate and never disguised as a proper measurement. Where no public sources existed at all was live hospital occupancy, ICU census, platelet stock, staffing. The platform says so with an explanation instead of showing plausible values. So this is because these data was actually not available island-wide, and it instead of making sure that we simulate or like post fake data as real, this has been explained in our model fairly well. Moving on, let's take a look at the engineering as what has been done right here. So the pre-processing is that every source gets normalized into one frozen schema, one row per district week, district IDs, ISO week, cases, population, and 4 weather fields. 2 administrative traps live here that silently corrupt results if you get them wrong. Sri Lanka has 25 districts but 26 reporting divisions. Kalmunai reports separately from Ampara and has to be folded back in, and Colombo Municipal Council reports inside Colombo district, not as a 26th district. Yet if you get either wrong, you silently undercount or double count a district every single week. Leakage and safety was a non-negotiable rule. The silent most way a published forecasting result turns out to be wrong is the evaluation leakage. The model accidentally seeing the future during training. We enforce 3 guarantees everywhere, backed by an automated test. Strict rolling origin, backtesting with an expanding window, so at any evaluation point, the model has only ever seen weeks up to that point. Every feature is a shifted training statistic, never centered window or a whole series average. And models are handed a truncated panel and own features inside. so there's no shared metrics leak through. The core test rebuilds features on a truncated panel and checks it reproduces the full panel build exactly for every earlier row. If any feature ever peeks ahead, this fails. Next, moving on to training and calibration. Stage 1 ships three forecasting models, a seasonal naive baseline, a Serima with Fourier seasonal terms, and a pooled light GBM quantile regressor trained across all 25 districts at once. We hand-rolled a genetic algorithm tournament, selection, crossover, mutation, elitism, early stopping to tune live GBM's hyperparameters, deliberately not using a one and off-the-shelf tuning library because a generic library's calibration or cross-validation split does not respect our non-negotiable rule. We also built split conformer calibration on top of live GBM because independently fit quantile regressors are structurally overconfident and an ensemble blend across three base models with blend weights the same generic algorithm searches for. Let's see what we found out when we ran it on real data. We didn't just build against the synthetic data and stop. We ran the entire pipeline against real notified cases and were reporting exactly what came back. Only real data of 194 weeks, far less than our synthetic test bed, is not a bug. It's what happens honestly when a boosted model has too little real history to outlearn a well-specified seasonal model. Serima and the ensemble beat live GBM on pinball loss as a result. When live GBM just show a real measurable win, its calibration conformer correction lifts its 80% interval coverage from about 0.56 to 0.75. We think that honesty is itself part of the submission, a platform that only shows you result when they're which are not just flattering but which are real. So finally, all in all, there are three stages. There are 4 scoped views, real government data, and automatically every week is leakage safe, evaluation enforced by tests, and honest reporting even when the fancier model loses. This is built to help the Ministry of Health get ahead of an outbreak instead of reacting to one, which is the only way that cases can actually stop. Thank you.